Okay, I'd like to welcome everyone here for today's sustainability seminar. My name is Nancy Holm, and I'm the Assistant Director here at ISTC and help organize the seminars along with Beth Moshage. This fall, our series is focused on water quality and water conservation. The schedule for all of the rest of the seminars for the semester is out on the table here or available on our website. And in case you can't attend the seminars in person, we do broadcast them live and record them, and they're archived on our website. Usually it takes a few days after the presentation for us to post that. So those are all available. So as we begin today, I'd like to ask everyone here, please silence your cell phones if you haven't done so already. And then for those online, we'll hold your questions to the end and answer them at the end of the presentation, but our speaker today said he will take some questions if you have them on a particular slide during the presentation, but I'll come around with the microphone to have you ask your questions so that we can get that recorded on our broadcast. So I'm very pleased today to have our speaker, Thomas Moshage. Tom is the Senior Process Development Specialist and Project Engineer at Carus Corporation in LaSalle, Illinois. Carus is the world's largest manufacturer of potassium permanganate, and it's a provider of chemicals and services for water and wastewater treatment, air purification, and other environmental applications. Tom has worked with Carus for almost 40 years and has held a number of different positions at their facility. His current role deals specifically with energy reduction, resource conservation, and engineering new and existing procedures and processes. So today, Tom will discuss the work that Carus has been doing on water conservation at their plant. So please join me in welcoming Tom today.
Right. That's good, okay. I would like to meet the person that you just talked about there because I don't think I'm that good. A little bit about me is I started working at Carus full-time when I was 15 and a half. My father worked at Carus also. My brother works at Carus. My father, when he retired, was Director of Manufacturing and Director of Purchasing at the same time. What he needed me for when I was 15 and a half years old is he would have me go to work with him sometimes at 2 o'clock in the morning if there was an emergency, or 9 o'clock at night, and have me go do the hoofing that he needed to have done, or check the things that he couldn't check anymore. And my role kept on expanding from that point forward. Like I said, or like Nancy said, I've been with Carus almost 40 years. It'll be 40 years in January. In my time there so far, I've held approximately 18 different job titles. So I've worked at the entire site. I worked in the lab as a quality control technician, analyst, as operations and process supervisors, maintenance supervisor. Another title that was yard services and distribution, offsite warehousing I did. So basically I've worked almost everything that you could possibly work in at Carus. My education is not anywhere near what yours is. I have a high school education and I have some college. But recently, within the last 10 years, I kept going back and doing some other things, and I became a black belt, a Six Sigma black belt, and about a year and a half ago, I got my accreditation as a CPE, which is a Certified Plant Engineer. Everything that I've done, I've learned by doing it, or hands-on. One of the roles I had when I was working at Carus was Carus went on strike. And they took me from a laboratory position and they brought me into the plant, and I became an operator and shift mechanic. Doing that allowed me to see a lot more very young at how things actually operate and how things are supposed to operate. I learned how to weld. I learned how to use a cutting torch. I learned how to change motors. You name it, run pipe. I did all that, and I was 18 at the time. It was a blast. Anyway, getting to the slide. Apparently, as you can see, Beth works for two different places, the ITSC and the ISTC. So there's an error right off the bat, and I apologize for that. The project champion that we had, was Dave Brown. The champion for this one was Dave because he was the unit manager for the Carus division, which is what this was benefiting. He wasn't necessarily my mentor, is just I had to put something there as a champion. Project team was my brother Ralph and Gary Motes. Gary Motes is our electrical engineer, and he's also our programmer. Carus is all computerized. It's all on RSView with PLC logic. And of course, my key contact. The agenda is the background, which is I just gave you a little bit of my own background. A SIPOC, process flow diagram, data collection, sustainability, and annual savings. If anyone doesn't know what a SIPOC is, I can tell you that. If you do know what a SIPOC is, then we won't go further. Would you like to know what a SIPOC is? Okay, SIPOC is just an overview, and you identify the different parts of what you're trying to do or map. So S stands for supply, I is input, P is the process, O is the output, and C is the customer. I'm going to have to probably move this away a little bit. I'm sorry. ISTC's goal is to conserve 1 billion gallons of water in the state of Illinois. They were expecting to fund 3 to 6 projects. We requested half of the overall project cost, and we received notification of the funding in June of 2014, and the total funding equaled $63,446, which we were really happy to get, and it was a little pat on my back that we were able to get it. Project charter for this, I'm going to read this to you. I know that you know how to read, but it's a way to keep on moving forward. So as of December 2014, our site was using approximately 1,360 gallons of water per minute daily, which is equivalent to just shy of 2 million gallons of water, or 675 million gallons of water a year based on an operating year of 345 days. We were being charged at that rate per 100 cubic foot, which included the city's 5% utility tax. 2014's estimated water cost at the time when I put this together was $720,000. We were tasked with developing a water reduction plan to reduce our water usage. The problem statement is this year we began a new water contract with the city because they decided that we weren't paying them enough already the way it was. The increase went to $1.14 per 100 cubic foot of water. If we continue to use water at our current rate, 2015's total water cost will be equivalent to a little over $1 million. This is an increase of $300 and some thousand at our current water usage rate. Our goal was to come up with a plan to reduce our current water usage. This project is phase 1 of an overall plan to accomplish this. Phase 1 consists of using spent non-contact cooling water from the Carus crystallizer hot well to feed our water softeners in the boiler house instead of using raw city water. The water softeners currently use on average 100 gallons of water per minute. Our water softeners feed our RO system. Our RO system feeds our boiler. The RO system, the majority of the water that's used there is for the boiler, but we also use that water in different applications in the process where we want very clean seal water for pumps. The cost of poor quality is the increased water costs equal $312,000. With this project's completion, we will save roughly 50 million gallons of water per year, or approximately $76,000 per year. The project scope is the water system source quality and crystallizer integrity at the hot well to water softeners that supply the RO system, which in turn feeds the boiler and the Carus seal water system. Out of scope, something we didn't look at all, was other water usage points throughout the site. Like I said, this is phase 1. Towards the end of the slideshow, I will present my next 2 phases of the water reduction plan that we're currently working on. The reason I use this is to show what the primary measure was and the secondary measure was. The primary measure is the gallons per minute of water used for the water softener. Secondary measure is total site water usage. The reason I say total site water usage is we do have a flow tube on our water softeners, but the flow tube is on the discharge of the water softeners, not the inlet to the water softeners. So I really don't know for sure. I really didn't know for sure how much water was actually being used. And when I get further into the presentation, you'll understand why I didn't know exactly how much we were using. So we take a look at the total site water usage, which is an accurate number. And when I started the system to when I shut it down and then back up again, I could see the shift in actual total water usage. This is the side pack as I talked about earlier. It's just really simple and it's straightforward. City water storage tank, city water in, gallons per minute. The next slide will give us a high-level process step so you can see what it actually is. And then what output is raw city water or recycled city water, gallons per minute, and a water softeners. High-level process steps flow chart is, this is a more in-depth view of what's actually taking place. The start of the process is right here. It's the incoming raw city water to our water storage tank. It then moves forward to water is pumped to the site through process water pumps in our pump house. The water goes in two different directions. One of the directions it goes to the pilot plant processes and the Carus processes, which is the pilot plant is like a second plant within our site. The pilot plant is where we make our specialty chemicals and our catalysts, etc. And they use a fair amount of water also, by the way. The other place that it goes is to the #1 old crystallizer hot well to feed the #2 crystallizer barometric feed pump. That barometric feed pump pumps to the, well, as you can see, the #2 crystallizer barometric condenser. It pumps there to help produce the vacuum needed there. Right here, as we come across, we come to this point. This used non-contact cooling water enters the #2 crystallizer hot well. Approximate flow is 650 gallons a minute. What goes into that is steam and intercondenser water for the crystallizer jets. And what comes out, that water at 650 gallons a minute just goes to the South Lagoon. A South Lagoon is a holding pond before it gets discharged into the Little Vermilion River. Moving forward, as part of this new process is going to do, is at this point, we check the water conductivity, and that's a continuous check, and we also make sure that we have a level in the hot well. Please.
Can you explain what the crystallizer is?
Yes. He asked, can I explain what the crystallizer is? The crystallizer that we have takes the permanganate solution that we've made in the plant and lowers its temperature and allows the crystallization to take place. The vacuum on the crystallizer is roughly 28 inches. So what happens is as the liquid is circulated through the crystallizer, the crystals grow and they drop out to the bottom in a suspension tank, and then we discharge those crystals to a centrifuge and then dry. Okay, so part of the new process is that the water conductivity is checked right there, and that we have a level in the hot well. If we were to lower the level on that hot well too much, the drop leg from a barometric condenser would become exposed, we'd lose the vacuum, and the entire contents of the crystallizer would just drop. And we would have an environmental incident. So we don't allow that to happen.
So is the conductivity checked to see if you have that problem?
He asked if it is there to see if we have that problem. No, the conductivity check is there is if for some reason we had an issue with the crystallizer and there's a carryover, the conductivity would immediately begin to jump up. And I have it set that it's at a certain point, so if it goes up more than 50 microsieverts, it will automatically shut the system down and switch back to raw city water so we don't pump contaminated water to the RO or to the water softeners and thus the RO and the boiler. Because I'll tell you, screwing up a boiler costs a lot of money. So if it's not good, no, the pump is shut down, the valve switch to feed the softeners raw city water. If it's good, we go to the right, water is pumped from the hot well to the water softeners. through a new pumping station. I didn't make that one box quite large enough, I guess. And then to the water softeners, and that's the end of the process. This is the proposed processed water flow. Here is the hot well that I was speaking about. What's in blue from here, or in the red wavy line, is the new process or the new lines that I put in to allow us to feed spent cooling water to the softeners instead of using raw city water. You can see there's the pump right here. We have the connectivity probe and a level controller. And then we have two automatic valves right here. That then pumps into the booster pump that then goes into the water softeners. This is a screenshot of part of our process, which our process, like I stated earlier, is computerized. Everything that we want to do, we can do from any one of the workstations that are in the plant. Once again, see that this is the new pump here, comes up, comes across, and it goes into the suctions of the booster pumps that then feed the water softeners. When we set this up, we have these hot well to boiler permissives where the pump will not start up unless all of these are green type of thing. The pump will start up. It'll slowly ramp up to a desired set point pressure, which is right here. It's got a variable frequency drive on the pump in order to maintain a certain pressure point that I need, because I need that pressure to be able to feed not only enough water, but at a pressure that will give us the required pressure on our booster pumps to make it through the water softeners, and then still be able to provide the pressure needed for the RO train pumps. So what happens is this starts up, the pump starts up. Please.
What is the difference in the conductivity of the city water going to the softener and the cooling tower process water that's going to the softener?
He wanted to know what the difference was on the conductivity or the water quality. I have a slide coming up next, or in the next few, and it will be one of the things that are addressed. I believe that's it for this one. So this is another screenshot of another part of the process, which, as you can see, here are the booster pumps that were shown in the last screen. And if we were on this screen right now and I clicked where it says city water crystallizer hot well, it would take me back to that screen. Everything's all linked together in our process that way. But this just shows our two water softeners. Right now, when I took this screenshot, we had 0 surface flow and 0 hardness, but it's going to the RO system. I'll explain why it's showing 0 surface flow in another couple of slides so you'll understand why it does what it does. Matter of fact, this one is right here. This is 217 days of gallons per minute water flow exiting the water softener. The little part here, it shows that the average is 101.35 gallons per minute for that entire time period, even when we had this one downtime right here. The reason it looks like it's going up and down so much is the water softener flow rate changes based on our RO storage tank level. As the RO storage tank level drops, the trains then kick on and they accept water from the water softener. When we reach the desired level in the RO storage tanks that we want, then the train pumps shut off and the flow drops down to nothing, basically. So it's a constant cycle of up, down, up, down. When we are pumping, we're pumping up about 220 gallons a minute through the water softeners to the RO system. Here's a histogram of the average daily water use from that period. As you can see, it's just a mean of 104.4 for this. I just wanted to show that it's fairly controlled. It's not, spread out. It's a normal curve. All part of the Six Sigma things that you have to include, which you don't really need this, but you could have done it with Excel data, etc. But we used Minitab on this. So I got a 2-sample T for the current and future water costs, just to give another mini tab thing. So what I did was I looked at 2014 and then the same amount of water for 2015 to show that there is a significant difference. At the 2014 cost would be roughly $160 a day for the cost of water. At the new cost, that same amount of water will be 230 gallons or $230 a day. So we get a difference of almost $70 per day, or a 43.5% increase in costs. Water project concerns. First one was water contamination from the crystallizer demister. We spoke about that. That was the conductivity part, right? Next concern was a hot well water level loss leading to vacuum loss in the crystallizer vaporizer, which is what I had spoke about earlier. Pump failure. Initial and subsequent system startup contamination concerns. Water quality, raw versus recycled. So how we addressed that was, this is where you were talking about the water quality. We had, I had our lab technicians test the city water for manganese, potassium, which is what would be there if there was a contamination issue, conductivity, TDS, and pH. So this sample of water, we also grabbed a sample of the hot well water at the same time. And there really isn't much difference between the two in any way. We have a slight increase in pH. We have a slight increase in conductivity, but actually we have a drop here. So I basically assume that there is no difference between the two waters that I would have to worry about, where I'd have then an issue with the water softener. And then with the RO system, if there was anything in there, if it was more of a significant difference, it wouldn't make any difference because the RO system would take it out. Sustainability. The following standard operating procedures have been modified to address the startup and shutdown and the bypass of the system. These are just more things that we did to make sure that I took care of the concerns that I had listed earlier. So you can see that there's plant startup after a full or partial power outage, etc. These are the new ones that I did, and then a new standard operating procedure and a complete lockout tagout sheet for full outage, so that when we go to lock out a piece of equipment or a process, it lists all the equipment and all the tags that need to be locked or valves that need to be closed. And our documents, our lockout tagout documents, are all picture related. So we'll actually take a picture of the pump or the valve or whatever and then state what needs to be done, and then they sign off on it and then do the verification that it is or it doesn't start, etc. Part of the sustainability also is now I track on a weekly basis water usage at the whole site at the different points that we're able to track them. So the information on top, all up here, this is an Excel spreadsheet, but it's tied in with PI. PI is our process information database. Anything that's happening in the plant where you saw the screen where you have a valve opening or a pump running or a pump running at a certain speed or a flow rate or a temperature, etc., our process information system gathers that as often as 1 or 2 seconds, 2-second intervals. Screen that you saw with the line that was just painted up and down, that was 217 days of data that I had pulled out that showed what we were using in the way of water. As you can see, since we started up, we got water being used for water softeners in RO system, 0. All the different places that we do use water, what I did was, this is a 7-day average, and then I gave the cost of that water for us for that last 7 days, and that's where we come up with the savings that we were talking about. And then I have a store data button that then takes the data, and on the second sheet it handles a complete running total, so then we can take that data and we can do whatever we want with it in the way of manipulating it. This is a PI screenshot of the system startup. What I was saying was PI, this is a trend screen that I can use getting the PI data pulling it from the system. The green one is our city water flow, which is our total city water flow, this right here. And you can see that it goes up and down, and it's directly related to our water softeners running also, as in the water flow through, or this is the operation of one of the RO train pumps. It comes on with a pre-flush, then a run, then a post-flush, and it's down again. This was the system startup right here, point. So you can see when I started up the new process, which was just now instead of city water, I'm using recycled, used water. You can see that our total water usage dropped from being up here to this point here. And then you'll also see that every single time the train pump comes on, it doesn't affect what's happening with our total water usage. So that's one of the proofs that I use to show that we're making a significant difference. Yes. He wanted to know what the y-axis on the pie screenshot was, and that was gallons per minute. And I used different scales. The green is 400 to 1,100 gallons a minute. The blue was 0 to 400 gallons a minute. And then the next two are just which softener is running at the time. So it's either 0 or 2. So I could show that it wouldn't fill up the whole screen. I made it 0 to 2, but it's actually a 0 to 1 number.
So is there a difference in the scaling? Because I see the bottom, when the softener does run, it is still running at full, whatever the previous GPM is. But you know, if you were to look at the jumps in the green line, they're not corresponding.
Well, they are, because it's like I said, it's scaled differently. So I can, what I do is when I build my pie troubleshooting screens, I build them so I can see what the process is doing. So the pie screen gives me the ability to have multiple scales for every data point that I'm looking at. So here's a 2-sample T from process startup. I took 420 data points before, showing our Carus total water usage, and then 420 data points afterwards to show that there was that significant difference and there was no change in our process. So we got an estimated difference at 122 gallons a minute with a p-value of 0. Just there to once again prove that the project is actually doing what I said it would do. Project cost, initial project installation costs, I had projected them to be $126,000. Actual was $132,000. So I was over by $5,977. One of the interesting things is when I was researching this and I had to come up with the appropriately sized pump and piping, I forgot to take one of the things into account when I sized the pump, and that was our incoming water pressure is at roughly 65 psi. I didn't take that into account. I sized the pump so I could pump 275 gallons a minute, but not necessarily at that pressure. Now, booster pumps need that inlet pressure going into their pump suctions to be able to up that pressure once again to function properly through the water softeners. So I was wound up able to use the correct or the same pump that I had bought, but I had to get a full-size impeller on it, and I had to go from a 1750 motor, RPM motor, to a 3600 RPM motor. So that was a jump in size of horsepower, which also meant that we had to change the innards of one of our disconnect to accept that increased horsepower.
What is the breakdown of the cost? What are the main components that contribute to the $132,000?
The maintenance labor that was used to install the equipment, and then the electrical labor, because we used outside contractors for the electrical labor and for the mechanical. We had roughly 250 foot of pipe that had to be run. We had to put in the pump base. we had to get it into the hot well without shutting down, so we waited until we had an outage when the system was down and empty so it could tie into it. And the smallest part of the cost was probably the instrumentation. And my cost is free.
How about when you do the projections? Did you just base it on prior experience? Did you actually get quotes from your suppliers?
He asked what I based my projection on, and that is exactly correct. What you had asked was, when we get ready to do a project like this, we have to do an AFE. It's an authorization for expenditure. Because before it gets approved, people want to know where's the money going. So I went out and I got contractor quotes for the mechanical end. I talked with my pump manufacturer or supplier, got quotes from him. So it's just a matter of getting all the quotes together, putting it together, and putting it on a cost estimate sheet, and then that number gets transferred to the AFE.
So if you don't mind,
I usually don't ever go over project costs, by the way.
so let's assume there is a line item for equipment. How much is, as a percentage of that equipment cost, how much is labor in this particular project and electricals? I'm just curious.
He asked how we break it down, and we have to break it down as in individual pieces of equipment, and then we also have to break it down to actual labor that is mechanical, then labor that is electrical. And that's based on the knowledge that I have of doing projects since the first project I ever did, I think, was 2001. And it was just, we learned by doing. And then we get help from people in our departments. My brother, for instance, helped me a lot when I was first starting out doing this. But it's just more of a feel. You go into it, you look at all your costs, you put together drawings, and then you move forward. So what we expected originally when I put this together was a savings of 104 gallons per minute, or 51 million gallons saved annually based on 345 days. 2015 water costs set at that. Based on data presented, this equated to almost $80,000 a year annually, with a 0.8-year payback based on the 50% funding from the ISTC. Now, this is what was expected. Now, getting to that one point I had said earlier where I didn't know for sure how much water we were using, well, normal water softener usage that we have two water softeners. So when one is in service, the other one's in standby. When the one that's in service needs a regeneration, the other unit comes on and it becomes active. It's the amount of water that we use doing the regeneration that we didn't track, because there is no flow tube on the discharge part of having a water softener regenerate. Because what it does, it goes into a slow rinse, brine draw, fast rinse, etc. So that's what I wasn't able to tell until we actually did the project and we weren't using New City water anymore. I could then do the comparison, which the final cost savings overview wound up being 122 gallons a minute instead of 104. We're actually at almost 61 million gallons of water saved per year. And then based on the water cost for 2015, that's an actual savings of $92,771 annually, with still a 0.8-year payback based on the 50% funding. So this is one project that I basically have it approved that we're moving forward with. It's taking what I'd spoken about earlier, the water that comes in, it comes into the old crystallizer hot well. Well, the water just comes in at a rate, and we have to maintain a level so we don't draw below and then pump air into the crystallizer. So we're at a constant overflow rate. And I measured it, what the overflow rate was, and it wound up being somewhere in the neighborhood of 110 gallons a minute of water, just coming in and not being used at all and going to the South Lagoon. By removing that hot well and putting in a water storage tank, which I already have there, it's the old crystallizer suspension tank, we just have to do work on it. I'll have the water going into there, and we'll have a control valve on the water inlet line so that we're never overflowing. So that'll save like 110 gallons a minute, and then I'm going to be taking the, we have a cooling screw as part of our process. It's a hollow flight cooling screw. Water goes in, water comes out. That water was just going to the sewer. Well, I'm going to return that water now to the new recycling or to the new water holding tank that I'm going to put into the process. And then we also have mechanical seals on a lot of our pumps. And we have a cooling pot on those mechanical seals. So we basically have water going through a coil that's in a little pressurized pot that cools the water off as it goes to the mechanical seal and back. So that water was just going to the sewer also. Well, I'm going to now send that back to this. So the total amount of water saved is 130 gallon minute, which equates to $99,000 a year of savings. The project capital cost right now, I put at $177,000 to do, which I've already got all the quotes and everything done for it. It's ready to go.
What happens to the heat picked up in the previous project as well as these projects?
He asked what happens to the heat, or, okay. What happens to the heat? Does it affect our process further on down the line? The amount of heat that we're going to pick up from those two small flow items is insignificant. We may see a 1 gallon per minute increase. Now, for the other part of the process, that hot well water runs around 83 or 84 degrees Fahrenheit. Our raw water coming in runs at about 64 degrees Fahrenheit. The interesting thing about using recycled water now is we've improved our performance of our RO system now, because the warmer temperature actually allows the membranes to work better. And then another side benefit of that is all the piping that was in the boiler house before during humid days would just be raining water down, dripping from all the condensation. We don't have any of that now anymore either.
So my question to you was going to be, did you figure in the benefit of the increased productivity of the RO system in your benefit calculation?
No, I didn't.
Because there's a specific energy savings there that you should be lowering. So the unit of power that you're putting into your RO system, you're going to produce more equal in water. So
he's saying his question was, and his statement was that I didn't capture all of the benefits of my project initially. And in my write-up, I didn't capture those benefits also. The last one is one that we're currently working on, our group is, and this is one of the few times that I've worked with other people like myself to do a project. I usually do my own projects. You know, they're my ideas. I get the okay to move forward on, and I do all the work. Well, this project that we're looking at right now, I'm part of the process development group. And the two guys that work in my group, we're doing this all together. It started out as a simple idea that kept on growing, and it really looks good right now. Recycled cooling water in the pilot plant, the other part of the process that we have, is under evaluation. What we'd like to do is use recycled water from the sodium permanganate crystallizers in the 400 feet tank and use that to then cool the north oxidizer, which we have to cool. The north oxidizer has to go from like 120 degrees to 80 degrees as a continuous process. And we've done all the rough calculations already, and we're looking at 114 gallons per minute of annual savings once again. So in the 2.5 years that we started doing this and taking a look at what we needed to do to reduce water, we've reduced water usage by probably 350 gallons, or we will when we do phase 3. That's it. You can wake up now.
Thank you very much.
how much water is used on site?
1,360 gallons a minute. I believe in my first slide, as part of my problem statement, was it? There. That's how much we use at the site, 675 million gallons a year.
And
How do I what?
So this 1,360 gallons, is it being charged to
It is being charged to specific product areas. Right, like the water going to the boiler house, that gets charged against the boiler house, which, you know, it has its own account area, as in with the gas that's used in the boiler house, et cetera, the treatment chemicals, the salt, et cetera, that's all charged to the boiler house area.
And do all product centers have the same unit cost for water, or will they be different for any reason?
It's the cost that we have for all the different cost areas are the same when it comes to the variable cost, as in raw materials or incoming or electricity. It's all one cost. Yes, sir.
I mean, I'm not a scientist or a researcher or a businessman, but I'm seeing the success of your process there. I wonder why isn't water recycled routinely in industrial processes?
Why? At the time, what we did before, water wasn't an issue, and water was cheap. Where you can see all of a sudden, after a very long contract that we had with the city, which was like 25 years so far, that the contract was up, and they decided to renegotiate the cost of water to us.
Is that what triggered the focus on the project? You just saw a sharp increase, and somebody went, yeah, you know, we need to pay attention to that.
He asked if that's what had triggered the sudden interest in water savings, and yeah, that's part of it. Plus, the other thing was I got an email from someone within the corporation that sent a notification from Nancy and Beth about this $1 billion water challenge, and so that's my job. I started in process development in 2010, and like Nancy said originally, was my focus is on energy, et cetera. Well, since 2010, I think I'm accountable for somewhere in the neighborhood of $1.5 million of annual savings because of the energy reduction and water. Yeah, I'm paying for my salary.
Is 2-year payback the general benchmark? That's always what I hear.
For us, it's 2-year payback is the benchmark, and the ROI. There's another number also, and I forget what that is. But anyway, if you don't hit that, the project probably will not be done. I actually did put together a plan to save roughly 50% of the water that we're currently using. The projects that I'm doing right now, we can do. One of the projects that I had come up with to save water to get us to that point, I just had to come up with the plan. The cost involved with putting in the chiller and the cooling tower and everything else along with it, it wound up being like a 6-year payback or something like that. So it just wasn't feasible. But everything that we're doing now is definitely feasible.
Do you make potassium permanganate just in the United States or also in other parts of the world?
We make it just in the United States. At one time, we were making it in Spain also because we had purchased a potassium permanganate plant in Spain, and we ran that for a little while to see if we could run it efficiently enough to make it profitable. And we found that we couldn't.
And is the plant in LaSalle, in your opinion, with that? So the plant, if you had to compare the plant here and the one in Spain, are they similar in terms of the way they operated? Are they very different?
Slightly similar. Carus's whole process is basically patented. It's all proprietary.
So
parts of the process are not proprietary because there's other people that use electrolytic cells to do their conversions, et cetera.
But the lessons that you learned in this particular project, would that be applicable to any of your other operations around the world?
Sure. We have a phosphate plant in North Carolina. We have chlorine up in Indiana and out in Reno. The things that we're doing that we're focusing on can basically be done anywhere. I'm part of what's called a VCR team, a variable cost reduction team, and it started in 2010.
And so do you see this permeating through the structure of the organization? Or?
Oh, definitely. Everyone is involved with the VCR, indirectly and directly. We also have 2 representatives from Ameren that are part of our team. Ameren does give wonderful rebates. We just recently retube our number 3 boiler and put in a high energy efficient burner and reactivated an economizer, which we had already put in a condensing economizer to get double savings from our exhaust heat. And we're realizing somewhere in the neighborhood of 275,000 therms of gas savings a year. And our rebate from Ameren was over 250,000. That was one of my last projects I did too.
How many times can you recycle the water?
As far as I'm concerned, you can recycle it as often as you really want to. I mean, some of our cooling towers that we have in the plant is a constant circulation loop, and the only time any new water is added to it is when we have evaporation to the point where the water level gets too low. With the RO system, it allows us to use water 40 to 50 times.
There's no discharge
From
your plant.
Oh, yeah. Discharges in water?
Mm-hmm.
Yes. Always.
What's the
Difference in water quality between the
All of our non-contact cooling water goes out of the plant. Then there's, storm runoff and stuff, and that also goes to our holding pond.
Okay.
Part of our EPA permit is to 24/7 monitor the water quality.
Okay, are there other questions? No questions online?
I hope I didn't bore you too much.
No, thank you very much for your talk. Very interesting. And we'll look forward to everyone coming back for our next talk in a couple of weeks. Thanks much.